Welcome everyone to the AI Engineering Bootcamp Cohort 5 session number 6. As we come into Thursday of week 3, it is time to put everything that we've learned all together in one big old build. We are talking multi-agent applications, and we're going to spend a lot of time building today. You guys have already been building, shipping, and sharing like a bunch of legends, so great work, everybody that got in on the action since we talked about it on Tuesday. Sonu, Deepti, Hugh, and Dirk. We see you guys keep crushing it, and I'm loving the people doing the advanced builds and sharing the great lessons. Even if other people in the cohort might seem like they're further ahead, this is a big deal. Learning finally the mechanics of Git. Way to go, guys. Chainlet being implemented and sort of what's happening core conceptually. This is so important to be able to extract these kinds of fundamental lessons. And we'll see this today in multi-agent systems and multi-agent RAG applications. A lot of you guys coming in hot with the homework 4. Love to see that. Keep up the great work, guys. And the lessons, it seems like LangGraph was before the agentic hype. Vinod, way to drop these the concepts of state and state machine. It seems like you guys are really honing in on some important stuff. And I really do love when people, Mike C does this a lot, throw back to an old technology shift. And we're seeing the same thing over and over again in the space, whether we work in startups or big companies. The technology is going through the technology cycles. So I love to see those analogies coming in. Keep up the awesome feedback on the homework as you submit it. That's the kind of stuff that creates value for people. Speaking of feedback, a lot of you guys really, really liked the last class. I wanted to just read this one. The problems from last time have been overcome, and I can understand most of the information. Let's go. This stuff is going to add together. It is going to continue to stack on it. And please, please, just give it a little more time if it hasn't yet. Today might be the day. I thought it was helpful to review and go to the next topic. We're going to keep these vibes going today. Good mix. Great. Okay, there was some feedback, though. We got some feedback on falling behind the rest of the group. We do our best to make sure that you have the API keys. I was a little late on the Tavily one, admittedly, last time. We'll make that mistake in cohort 6. However, if you are truly feeling behind the group that you're in, there are other groups that you can join. That is, unless maybe you're in Robert's group already, you might need to just stay there and work it out. But if you're in any other group, there are other groups you can try out, and those might be a better fit for you. We're still only 3 weeks into a 10-week cohort. I know you guys are developing some great relationships, but if you'd like to just try it out, try something else out, you can let us know in the feedback, and we'll definitely work with you on that. A lot of other feedback suggestions coming in. Love these. Some images for some of the concepts. I'm always trying to do this more. Tell me which concepts you want. And everybody wants more examples. Everybody wants more end-to-end applications. As you'll notice, what we're going to start to do, especially today, is we're going to say, hey, listen, this is an engineering course. We're going to do a lot of engineering. And as you know, engineering is the solution. It's not talking about the problem. It's not talking about the story of the problem we're solving so much. So we're really not going to be able to spend a ton of time on use cases. We can only pick 1 or 2 per session, and I can pepper some in throughout. So if there are specific things that you really want to know, please double click in on this for me on the next piece of feedback that you leave. Hungry for more examples, more recipes. These are coming. We're going to go deeper into RAG, deeper into agents all throughout this course. A gallery of the advanced builds. I love this feedback. If more people had done advanced builds in previous cohorts, this might be something that makes sense. We're a small bootstrap startup. If you're an advanced build person, I would love for you to kick this project off with this cohort. I'd like that we cover more complex scenarios. Yes, we're going to continue to cover more complex scenarios. But we are going to try to always keep it simple. It's always going to be less complex than some of the stuff in real life. This is an academic type thing that we're doing. We have to make these things fit into small boxes that are doable and don't totally overwhelm everybody that touches them. So if you want more, we're going to keep pushing the advanced builds. Let us know what you think about those, and let us know if you want to go even more advanced. Some people love the speed. Others think it's a little too fast, or we want to slow it down. I've asked Wiz today to really take his time on this first demo because it brings together everything and really make sure that you guys are grokking this. So hopefully that helps out, so you can really feel like you're up to speed after 3 weeks. This was great. Get the full time and breakout room, super important. I'm going to honor this. Absolutely. It's at the top of my list every single class. Great discussion. If we could go slightly longer, that'd be great. I'll tell you what, the thing is, we can't. We understand that you're working full-time. Well, so are we, and so are our peer supporters. And we always meet before and after class. And this is why fundamentally, this is sort of a very long thing that we do already. And, quite frankly, I don't pay the people who work for us nearly enough. So thank you for helping us squeeze it into 2 hours. And thank you for peer supporters, always peer supporting like a bunch of legends. As we grow, maybe there's opportunity there, but it's just not something we can do today. But thank you for that feedback. We'd love to learn about integrating knowledge graphs in a LangGraph self-reflected RAG flow. Hey, Wiz, what do you have to say about that? That would be dope. But, definitely we've got the tools in place that you could do this, right?
Yes. So basically, we can do, especially after tonight, we're about to be able to do any combination of all kinds of things in LangChain LangGraph universe. This doesn't mean that, it's all we're going to be able to do, but certainly you can start cobbling together all kinds of very fun, very interesting things. Whether or not you are excited to, integrate knowledge graphs is a slightly different situation.
Yeah.
But yes, you can. And in fact, we did an event today where we used knowledge graphs with from our friend Ragus, right? So yes, absolutely, you can use knowledge or integrate knowledge graphs. It's just going to be, your amount of excitement about that might vary from person.
Yeah. But if you love knowledge graphs, maybe you should hit up Don Branson, who took one of the past cohorts with us. He is always crushing them knowledge graphs. And he shows up in the Monday meeting too, by the way, quite often. So maybe you can meet him there. I'll see you there. All right. Thanks, Wiz. And then feedback shout out, Cat. Great vibes. Love it. Let's go, Cat GPT. All right. So let's get into it today. We want to align our aim. We know that we are in this agent and multi-agent space. So what I want to do is I really want to focus for about 10 minutes introducing the build and introducing multi-agent systems to you. We want to understand what they are, want to understand how they work. And we want to kind of see that they're the same across frameworks, although we're not going to dig down into all the details of every framework. It's just not simply something that's going to be particularly useful to you, but it is something that your breakout room peer supporters are ready to discuss if that's really of interest to you. All right, multi-agent systems, and then we'll get building. Let's talk about multi-agent systems. Let's break this down from like true first principles. All right. What's an agent? Well, let's think about it classically first. This is where we must begin. It's like the text on AI. And literally, AI itself is defined as the study and design of rational agents. Now, this word rational is there, and we must address it. What does it mean? It means probably what you think it means. It means we're doing stuff for a reason. It means we are reasoning. Look at that. We're going to see a lot of keywords here as we navigate the classic and the modern views. An agent, according to the classic book that's called AI, A Modern Approach, is anything that can be viewed as perceiving its environment and then acting upon that environment. By the way, author Stuart Russell, Peter Norvig, I highly recommend you guys check out Stuart Russell's book from 2019. This was sort of a deep cut putting this together, and I remembered, oh yeah, I did write a little bit about this book a while ago, maybe almost 4 or 5 years ago. I do think this is one of the #1 books that can be kind of broadly recommended to anyone. Know that he's just the OG in the game. He wrote that book, and then read it through that lens. Talks about the control problem, talks about all sorts of fun stuff there. Again, another classic idea here, if we go to the Alan Turing Institute, they will define a multi-agent system as a multi-agent system is something that consists of multiple decision-making agents which interact in a shared environment to achieve goals. Okay. Fast forward to now. Everybody knows Chip's book just came out, December 2024. It's now sort of the handbook for AI engineering. Shout out to Chip Wayne, crushing it. She published a book on machine learning system design a couple years back, and now this is really kind of leading the industry. She says an agent is characterized by the environment and the set of actions it can perform. An AI agent is meant to accomplish tasks. Environment, action, tasks, goals. Okay, now, what did we just see come out? Shout out to Kenny for dropping the app and having me do the little rag on the computer using agent from OpenAI just came out. Guess how it works? Well, you won't be surprised to see that it's perception, taking those screenshots, reasoning, looking at current and past screenshots, and actions. What are the actions? Clicking, scrolling, typing. The computer using agent operates in a loop. It's kind of hard to see where the computer using agent is here. We'll come back to that. In an AI agent, Chip tells us, AI is the brain that processes the task, plans a sequence of actions, and determines whether the task has been accomplished. Remember, we have talked about agents already. This is kind of the brain. The agent in the computer using agent loop is kind of this whole thing, actually. I can't quite locate the agent, which this makes it hard to talk about agents sometimes when you can't see them. A lot of times we'll see loops that look something like this as well. The LLM is labeled as such, but really the LLM is the agent, and it's got access to a bunch of tools. In fact, we already know about this because we've already learned about LangGraph. We've already learned that agents with access to tools can solve problems. Well, if we go to something like a crew AI, for instance, we're talking about the same thing, although probably we need to specify the exact task here rather than just the general problem. That planning piece is going to be a little bit more flexible in a LangGraph. LangGraph tells us it's a library for building stateful multi-actor applications with LLMs used to create agent and multi-agent workflows. Stateful agent applications. Well, agent workflows just came out from Llama Index on the 22nd last week. What do we see here? We see our good friend stateful agent applications. Remember, agents are a pattern. They are not a specific thing. What kind of pattern are they? Well, they're the reasoning action pattern, or you might say they are the perceiving reasoning and action pattern. We ask a question, we can take some actions, we're going to reason in that conversation thread. We might know the answer straight away, but we might need to go hit up some tools. And as we hit up tools, we're going to observe stuff and we're going to put those observations back into the conversation thread, into the LLM's context, into the agent. All right. And so from the paper, the React paper, reasoning traces help update and induce, track, and update model action plans. Actions allow us to interface with external sources or environments, right? Environments like maybe our virtual environment or this GUI setup we see in computer use or computer using. Whatever you call it, whoever you get your computer using agents from, it's the same thing. It's an agent. It's got some tools. Screenies. You can move the cursor around. You can click buttons, right? And what happens when you do this? Well, we've talked about this already. When you are doing this kind of thing, you're actually doing reasoning and action in one step. This is called function calling. This is called tool calling. This is combining React. That's what the LLM was fine-tuned to do. We want to give the LLM access to tools. When we give the LLM access to tools, we have to call them with a function. And so really what we see is when we see something like computer use from Claude or computer using from OpenAI, we see at the bottom, it's kind of like React and then function calling and then toolbox. And, you know, we've talked about what agents are a lot. Let's go back to our fundamental definition. A system that can leverage or emulate reasoning to make dynamic decisions in an application flow. Let's extend this to multi-agent systems. It's a system that can leverage reasoning from multiple independent agents to make dynamic decisions in an application flow. So the question comes, why would I need more than one agent? Well, you need more than one agent. Imagine you had all the tools in the world and you had an AGI. Do you really need more than one agent? Well, when the reasoning machines need to be specialized, if the task is complex, we can develop multi-agent solutions that sort of match or map to that complexity. Remember, we want to sort of achieve this complexity, but we want to do it through a kind of simple approach. We want to find simplicity through complexity, let's say. So often, while we might be able to put a mega prompt, we're often putting simpler prompts with multiple agents. Even though we could give it all the tools, maybe we're giving different agents different tools. That's going to give us reasoning traces set up differently through our application. Maybe we want to do fine tuning. This is great when we want to group tools, responsibilities, separate prompts, have easier conceptual models to share with our boss. Could be very interesting, could be very useful. All right, so agents are giving the LLM access to tools. What about multi-agent systems? Well, multi-agent systems, exactly right. It's the same. It's just function calling all the way down. So let's build today. Let's build with LangGraph. Let's build some stateful multi-actor applications with LLMs. And let's look at the couple that they have on the LangGraph repo. Okay, this is a great place to start. Multi-agent collab, hierarchical team, agent supervisor. Multi-agent collab, what do you think that is? It's multi-agent collabing, okay? It's not that exciting. The supervisor setup is quite interesting. This one is the supervisor is there, and the supervisor decides where to route to which agent. I mean, after all, supervisors are just routers. Remember we talked about cognitive architectures, including the router? It means go here and then proceed to this output. Well, we can actually stack supervision into hierarchical teams. So we have a supervisor, and then we have like sort of lower level supervisor. So we got like, you know, big boss and middle manager boss. This is why middle managers maybe should be a little bit scared about the future of AI. So, you know, the supervisor is just a router. We can see it, just a router. Multi-agent systems are generally today, we're going to see routers on top of agents. Okay, you could imagine more complexity with different collab setups, and certainly you can build those. but generally we're going to see supervisors on top. The router is just a function calling agent. The supervisors are just function calling agents. Really, we're just function calling all the way down. So what are we going to function call all the way down today? Well, we're going to build AI Makerspace editorial. We're going to put a supervisor on top of a research team and a document team. We're going to do the hard work of building the research team and setting this up first. The goal, write a super dope LinkedIn post on an archive paper. We picked one out. This one's on long context, RAG, and we're going to build a research team with specific prompts to accomplish this. Wiz, walk us through soup to nuts how to set this up and build our very first team. And the second one, we'll come back and build our second team and set up our supervisor. Over to you.
Oh yeah. Okay, so this is a big one, this big notebook. So we're gonna take our time. We're gonna go through at a reasonable pace. That's just what it's gonna be. Okay, so first of all, there are two things we've got to pay attention to. Number one, we've got a graph, right? But that graph is actually a graph. So our at the end of the day, we're going to have a bunch of graphs, and they're all going to have be connected in some fashion to each other. Now, I would say the key thing to remember is that everything in LangGraph and LangChain is runnable, right? So this is how we're going to exploit that. We've been kind of saying it, right? But we're about to leverage that fact for the first time. First things first, you're going to need to do a bunch of installs. Now, in this case, we are not going to use a local collab. We're just going, or sorry, a local notebook. We're just going to use Google Colab for this assignment. There's some potential file permission issues with Mac that we're not able to make sure everyone can have a fun time. So we're going to stick to Colab where everyone can have a fun time together. Okay. Next, we are going to get some quadrant. We already know it. PyMu PDF parses PDFs, and then tick token. Tick token is a way for us to count tokens from OpenAI's models. Even though they're not open source models, they were kind enough to let us know how them tokens do. Okay, and those of you who are getting some 404s in the chat, if you just remove the word staging from that link, it'll work, and I will make sure to send you one that's ready to rock as well. Okay, so we're gonna need two OpenAI keys today. The first one is our favorite search, which is Tvili. Tvili just works, and that's why we're choosing Tvili. We're also going to use OpenAI Classic. We already do that all the time. Okay, we're building a RAG chain. Now this is important because we're building a RAG chain. That's a chain that we're making with LCEL that's going to do retrieval augmented generation. The reason we're doing this is mostly just to showcase that we can use all of these parts composably, or we can compose them together, right? They're all the same thing at the end of the day when it comes to what we're trying to do. Okay, so with that, we're going to set up our RAG chain. Now, the first thing we need to do is get some docs. So we're going to load those, and we're going to load those using PyMu PDF loader. It's just an okay PDF loader. That's why we're doing that. Then we're going to chunk each of these down to size. We're going to count by tokens because we know we're going to care about tokens, right? There's a certain number of tokens the model can handle at once. And so this is the idea. Okay. We're going to split them into chunks of 300. This is largely arbitrary. You can split them into whatever you'd like. We're going to use the recursive character text splitter. That's because you can see here we're using a paper, like a research paper, and we have this very handy format, right, in the research paper. Everything is partitioned by paragraph. and then there are larger line breaks between our headers. So recursive character text splitter, what it's going to do is it's going to let us chunk first by these double new lines, then by single new lines, then by our spaces, so that we keep as much information together as humanly possible. And one thing that I want to just point out, we're saying tokens here, not characters, which is important because when we use characters, for instance, right, we might run into situations where we lop off half of a word. That can potentially happen. With tokens, we at least know we're going to keep our tokens together. That doesn't mean that there aren't going to be some instances where we still lop things off, right? We might wind up in a situation where we keep important, right, but not Lee. But the idea is that those subword tokens are less information, so it shouldn't be bothering us. There's a great question in the chat, which is why chunk overlap, right? What is chunk overlap doing? Greg has linked an amazing tool that helps you visualize this. But the idea is that if we say split this paragraph into 2 chunks, we might want to make sure that each chunk keeps some extra information. So like, let's say we split it on the batch size as 8. What we'll do is instead of starting our next chunk at gradient checkpointing, right, we'll start the next chunk at the batch size is 8. And what this does is it helps make sure we're not losing information on the edges, right? Remember when I said about we might lose the Lee of importantly, right? With chunk overlap, you're less likely to run into that scenario because you keep some fuzzy space around your chunks. We don't care about that for this instance because we're not we're fairly confident that this is going to be an effective chunking strategy. But in situations where you have very long run-ons of text, let's say, you might want to consider overlap. And of course, you should use the tool to check it out. So we go from one paper, which is many pages long, to 15 chunks. Very good. So now we have 15 documents. This is the basis, right, to all of RAG. We take long document and we turn it into a bunch of small documents that we can shove into the LLM over and over again. Okay, in order, though, to do this part where we do RAG, we must, of course, use our embedding model. Our embedding model is going to be text embedding 3 small, very good embedding model. It's fast, it's cheap. We're just going to use it. We're going to use quadrant in order to store all of our embedding vectors. Remember with quadrant, right? The idea is we're going to feed it those 15 chunks. We're going to feed it our embedding model. We're going to leave the location just as in memory for when we're doing these assignments. But it's a one string change to get away from that, which is great. And then a collection. Now, a collection is an important concept, right? We've talked about it a little bit, but the idea of a collection is that it's like a subset of data that's in our quadrant vector store. We can have, say, many collections in our quadrant vector store, but we only address them when we address the specific collection. So this is a way to keep our data a little bit separate, and we'll learn a little bit about some metadata filtering in the coming weeks, which is going to help understand why that's useful or important. Then we're going to make this thing a retriever by using .asRetriever. Everyone loves that. And then we're going to create a RAG prompt. RAG prompt, nice and easy. You're a helpful assistant. If you can't answer the question, say you don't know. Classic stuff. We feed it in the model. We love that. We're going to use GPT-4o Mini for RAG. There's going to be a lot of questions about, like, when should we use which model? Now, the basic intuition is the more quote unquote responsibility or decision making power a model has, the more we're going to care about using a quote unquote a smarter model. Okay, so when we look at the actual model we're using here, it can be very weak, right? Comparatively, GPT-4o, I mean, it is still a really good model, right? But it's like it's old by today's standards. But the idea is we can use this small model and get away with it because all it's got to do is RAG, right? It's making zero decisions. It's just like, feed me some context, bro. I'll answer your question. So that's why we're using GPT-4o Mini. And then we make our RAG chain. This RAG chain made an appearance in our first Langsmith optional notebook. If you want to know all about what exactly is happening in this RAG chain, you can refer to that assignment. There's a picture, there's comments, there's pros. We dive deep on this particular chain. But the idea is it doesn't matter, because at the end of the day, we invoke it like we do every other runnable LangChain, right? So we invoke with our question, what does the context and long context refer to? Easy peasy. What does it refer to, right? Okay. We're going to go to this idea that we have a limitation with our RAG setup. And that limitation is it don't do so good if we want to look at a different paper, right? Because it's just one paper. We've hard coded it. So a bonus marks, don't do this in your breakout rooms, right? But for homework, you can attempt this activity, which will be, how do we fetch papers dynamically? You can look at archive, the archive tool for that. And we just looked at how to make a dynamic, agent, that tool calling agent on Tuesday. That's going to be very helpful if you want to do that. Okay. Now we're going to do a wall of imports. I try to never do this, but there's just so dang many. So we're just going to get them all out of the way. We need a bunch of stuff. Sorry about the wall of imports. It is you can minimize it if you don't like looking at it. There you go. Okay. Next up, we're going to have our first node, which is actually not a node, but a helper, because we have to build nodes. We're going to be creating so many nodes that we want a quick way to just, crap them out, basically. So we have this node helper, which is going to basically allow us to use this node over and over again with different agents that have different names. This is important. We're going to leverage this a lot as we go down. And then we're going to have our create agent helper function. Because remember, we're doing multi-agent now. So all of our nodes are agents, right? It's no longer just the case that we have one agent. It's all the agents all the way down. So we have our create agent, which is going to simplify the pattern that we used on Tuesday, right? So on Tuesday, we created the graph, the tool node, we married them together. That was great, but there's a faster way. So what we do is we have as inputs our LLM, which is going to be our brain for our agent, our tools, which is going to be all the tools it has access to, and then our system prompt, which is going to be, you remember from previously, system prompts like instructions. How should you do things, right? How should you approach this problem? We're going to tack on to the system prompt a thing that makes this work in all of our graphs. So we know that each agent might have its own system prompt, but we need them all to know how to do this thing. And so we give all of our agents this knowledge. We create a prompt template where we add in our system prompt. We add in our messages, which are going to be a placeholder since we don't have any messages to start. And then we're going to have our agent scratchpad, which is a way, it's like halfway to memory, agent scratchpad, right? It gives the ability for the agent to do some kind of work in a scratchpad to make better decisions. We're going to then create a OpenAI functions agent, and then we're going to wrap that in an executor. So our agent here is going to be just like what we did on Tuesday, and then we're going to give it access to execute the code for the tools for our agent executor. It is the thing that executes for the agent. There you go. Okay. And then we return that final executor object, and that's going to be our agent. Then we have to create a supervisor helper function. This is going to be where we create our supervisors, because we're going to have 3 supervisors, right? We have 2 teams, and then we have someone who supervises both of those teams. So our supervisor helper function, very straightforward. It's just going to be basically a prompt. It's going to take in some number of options plus some list of members, and then it's going to call which of those should be next. So this is going to be something that we run into a lot. This doesn't seem that hard, right? It is simply it's like a classifier. Who comes next? Where do I go next? Who's the next guy, right? But you'll find that the strength of this agent, right, of the model powering this agent, to be more clear, is very important, right? Because this is not the easiest decision to make for the LLM. It's got a reason about why it should do this, right? And so we use a bigger model for our supervisors. The idea is that we have some list of options of where it can go next, always including end or finish, and then we have some members. The members are going to be provided through our function, and then we have this function def. Every time we use tool calling under the hood, this big ugly blob is what we're really using. But that big ugly blob is big and ugly, so we don't often look at it with our eyes. We hide it behind some abstraction. But for this case, it's always fun. Here it is. It looks like that. It's basically just describing our function and exactly how we want to call it, but with JSON. Very, very cool. Then we have our prompt. Our prompt is exactly what it's always been. We add our system. We introduce this placeholder, and then we add another system of where it should go. Perfect. Then we're going to return a chain, another LCL chain. Let's go. We're already at 2 LCL chains, which is going to chain our prompt into our bound functions. Now it's just going to be one function, which is going to be the function that determines where to go next, that we're calling route. And then it's going to return that as a JSON output parser. This is because the models are smart enough to give us valid JSON back. This is extremely important because we need valid JSON in order to reliably inspect what the response is. Okay, so that's all the helper functions for our thing. We're now going to talk about the actual first team, our research team. They're going to do a lot of the work. These are our grunts, right? We're going to first start with the tool. Same as we did before. It's just Tavili. Everyone loves Tavili because it's just Google. There you go. Okay. And then we're going to create a new tool. You'll notice that this time, instead of kind of going out of our way to make a tool, we're just going to use the @tool decorator. Decorators are back better than ever. And what we're going to do is we're going to use very specific type hinting in order to give the LLM additional information. We're going to use our doc string in order to give our LLM information. And then we're going to finally just return our desired work to be done. You'll notice that this is our entire other chain. So this is the RAG chain we created above. We call .invoke on the question, and we return some kind of response. There you go. Okay. We could use a LCL chain directly, but we're going to use this wrapper because we want it to be a tool that can be bound to our tool node. Okay. Now we have our state. Before, when we did our agent, we just had our messages, but now we care about a few other things, right? Our team members and who is next. So we add those to state. There you go. All right. We're going to use GPT-4 Turbo as the LLM that we're using. You'll notice that we're using a bunch of different LLMs here, each of them tailored to their task. This is important. We have a question, right? Why is a powerful LLM important for this use case? We kind of already talked about this, but answer this in the breakout. And then what tasks must our agent perform that make it such that the LLM's reasoning capability is potentially a limiter? And that's, we've already kind of discussed. Answer it in the breakouts. Okay. Then we're going to create our search agent, which we're going to do through our create agent helper function. We pass in the brain, we pass in the tool, and we pass in what they should do, their system message, right? This is their directive. And then we're going to create a search node, which is going to be using functools partial. Don't worry about this, it's just Python, but it's going to wind up with us having a beautiful little function that we can use to call our agent, which we'll use as a node. We're going to do the same thing for RAG. We instantiate it in exactly the same way with create agent, the retrieve information, easy peasy. And then we have our research team supervisor agent. This whole blob is its system message, and these are the potential nodes that it can go to. So this is its members, as we discussed earlier. Then we can finally start making our graph. Our graph is started with a state graph. We're going to add our search node. We're going to add our paper information retriever node. We're going to add our supervisor. So we got 3 nodes on our graph. Then we're going to tie together our search and supervisor and our paper information retriever and supervisor. This is because we always go back. We always go back, right? Every time we get to one of these workers, we go back to the supervisor. That's all this is doing. And we'll look at a picture of it in a second. Don't worry. Then we have our conditional edge, which goes from supervisor to next, as determined by the function that we created above that we attached to our supervisor. There you go. Okay. We're going to then make our entry point to supervisor and compile down our grapharino. We then have our display graph. Our display graph is going to be just displaying our graph, but in a mermaid chart. Let's look at it. So we come into the chat prompt template. We go to OpenAI. We output a JSON function parser. We go to search. If we go to search, we always go back to the supervisor. If we go to paper information retriever, we always go back to the supervisor. Over and over again. We are always going back to the supervisor, right? It's hopefully not like you at your job, but everyone's had jobs where everything you do, you go back to the supervisor, right? So same. All right, now we're almost done. We're almost there. Okay, it's been a little bit, but we're almost there. What we have to do now is just wrap this in a way that makes it easier for us to use. We're going to talk about the fact that these agents don't all have the same state, but they all need to talk to each other, right? So this is just a precursor to that. The idea is to get into our chain, we're just going to provide this enter chain function, and then we're going to use LCEL to chain from this function into our full research team chain. And now we can go ahead and we can use it, and we can have it do the thing. We ask, what are the main takeaways from the paper, extending Llama 3's context tenfold overnight? And then we get, hey, I'm going to use search. I'm going to search about it. I'm going to get a response. Very cool. And then we're going to finish. Very good. That's what it does, right? That's the idea. That's all of that preamble was to get us the thing that says, hey, when I use you, please do the thing that I've asked you to do. And it does. We get information about the paper. We're happy to have information about the paper. This kind of funky syntax is not necessary at all. It's just so that we get to see exactly what's happening at each step. You don't have to do this when you build an application. In fact, you probably shouldn't do this. The idea, though, is that we want to see what's happening at each step. Okay, and then there's an activity for you guys. Draw the flow. So take your graph, draw what route it took through the graph, and then question 2, how could you make sure your agent uses specific tools? Are there any ways to set concrete flow through tools? We already know these. You just have to put it down on paper. With that, I'll pass you guys back to Greg, who will get into our first breakout rumorino.
All right. Thanks, Wiz. And, is it true that the supervisor needs to be smarter than the individual contributors in our multi-agent system? Or maybe not. Maybe sometimes. Maybe you just try it out. Maybe you just mix it up. Maybe a little DeepSeek here, a little polygemma there, a little. Like, how do we decide when we're building multi-agent systems which agent should be smarter? What do you think?
What it comes down to at the end of the day is just that, like, they all kind of need to be smart. Yeah. Which is unfortunate, but
they should all be the smartest they can be, right? You want the best team. You want 8 players, baby, right?
You want the best team. But right? Someone said earlier, right? Oh, just always use R1. R1 is terrible at most tasks, right? Like if you want to do simple RAG, don't use R1. It's overkill, right? If you want to just know something quick, R1 is not the guy, right? So what you want to do is the amount of responsibility, which is not a well-defined term, right? But we can think about it as number of potential decisions to make, impact of decisions to make, right? The amount of responsibility for each agent should be the thing that gives you a hint as to how, quote unquote, strong the model that you're employing is, right? So when we talk about our supervisor's got a lot more responsibility than our RAG node, right? RAG node don't care. It's just like, it's going to get docs. It's going to give you an answer. Very good. But the supervisor has to choose, when do I go to tool A or tool B, right? And this is the part that requires more reasoning.
And IRL, right? I mean, supervisors literally are optimized to do that exact job, right?
Yes.
I know everybody
And
on the team. Which am I going to send to today? Right.
that's a really important point too, that we're not explicitly saying, but is true. A lot of these systems can be just memed away by a smaller model that's trained on a large volume of data,
That's
right?
right.
Like if we have a really good classifier, it's gonna know where to go next all the time.
Yeah,
But when
yeah.
we first make our application, we have no data. And so we need to wait for the big old pile, right?
Yeah, yeah. And when they're just robots, they're just gonna go down the hall and just tap them on the shoulder. Hey, how's it go? What does he do? What does she do? Okay, let's go ahead and get into it, guys. 25 minutes, breakout rooms. Let's build our setup. Get the supervisor in next time. Get the document team in next breakout room. This one, we're focused on the research team, but we gotta get the setup. 25 minutes. We'll see you back for a quick break. Have fun, guys. All right, back from first breakout room, back from the break, and it's time to go ahead and get into the next part of the sesh. Don't forget, there's always one-on-one support available if you need it, no matter when the breakout room is. If it's first or second in the session, you can always go click breakout rooms and join here for support for some one-on-one help. Okay. Now it's time to build the rest of our pipeline. One of the things that's interesting is everything that we build is kind of just a prompted LLM. All of these Lego blocks of agents and all of these different pieces of our team, we're kind of just giving it a role, a persona, we're giving it an instruction, we're following the best practices of prompt engineering. And so it's helpful to look closely at the prompts of each of these. You're a supervisor tasked with managing a conversation between the following workers. Given the following user request, respond with the worker to act next. Each worker will perform a task and respond with the result status. When finished, respond with finish. You can kind of get some intuition about why you would want to actually put a smart LLM here, right? It seems like a complex space. And remember, supervisors are just routers. Now, which team should I choose? We kind of had this discussion in the break. I'm going to Tavily. I'm not necessarily going to Archive. Well, let's imagine that we have a writer, a note taker that's kind of doing research, a copywriter, and then like finally we have a dopeness editor. Now, in this case, you could imagine wanting to go maybe in a specific sequence, right? Or maybe not. These are the kind of interesting questions we can ask as we build these things. We obviously want to make sure that everything we produce is super dope. So we have a dopeness editor on our team. You're going to have to decide what you're going to put on your teams. And, you know, as we sort of think about how all of these are just LLMs and they're prompted, you know, from the IC level to the kind of middle manager level to the top level, you know, it really does help to always go back to what's going on in real life. What am I trying to sort of automate here? And it's not surprising that many of these multi-agent applications have not made it to production yet today, because really, when we talk about useful things that agents can do, things like these computer use agents, we talk about things like the research team that we just built, right? It's just a single agent with many tools. So a single agent with many tools can do lots of cool things. When do you really need a multi-agent system? This is an important question we should all be asking anytime we set out to build one of these. That said, if you just want to build a super sweet, mega dope multi-agent system for demo day, you should definitely do that. And we're going to show you how to finish it up and do it right now. We're going to get even more agentic whiz, show them how to build and stack the hierarchy to finish out our multi-agent build for the day in LangGraph.
Okay, so this is we're getting real. We're getting super real now. What we're gonna do is we're gonna go ahead and share the old screenerino here so that you can see it. Yes, okay. the big thing that we want to focus on is that this is going to be a just a collage of everything we've ever done before. So, last time we had, we kind of got into it a little bit. This time it's going to be everything. So we're going to start by setting up a whole new set of tools, a brand new set of tools. This set of tools is going to be able to manipulate your file system. Now, not your file system, because we're in Colab today, but it's going to be able to manipulate Colab's file system. This is a very useful thing to be able to do. So that's great. We're also going to need to toolify the ability to write, edit, and manipulate the file system. So what we're going to have is we're going to have a tool that creates an outline. We're going to have a tool that reads a document. We're going to have a tool that writes a document. And we're going to have a tool that edits a document. Now, you'll notice the actual implementation of these things are not as complex as you might think, right? Like this one is just like opening and then writing content to a file. This one is just, reading a file. Okay, very cool, very cool. This one writes things out to a file. Okay, we get it, right? They're very simple, but it's a powerful pattern because it helps us do things that leave some kind of, artifact, right? That leave behind something on our file system that can be used later. Now, is this a kind of memory? You might ask yourself. Maybe, almost, maybe, but probably not. So what we do is we have all these tools, right? Edit document, write document, read document, create outline. All right, scrolling like mad, but the idea is that it's just these tools. Very simple. Then what we're doing is we're looking at the activity, which is going to be describing what each of those does. I'll give you a big spoiler. If you're really struggling, you're like not a Python person, right? I bet there's some tools that would be able to assist you in understanding what this code is doing. But think it through first. Document writing state, it does what it says. It's just the state that we're going to use for a document writer. Now, notice that this is different than our other state. Our other state ended here, right? Our research team state ended right here. Didn't have this current, what's going on in current files, right? Well, current files is an additional piece of state that we'll need for a document writing team. The idea is that we have the ability to have different states for different graphs, even if they wind up sharing some of that state. All right, now we have this prelude function. Don't worry about it. All it does is it sees what files are currently in the notebook's file system. Okay, for a specific directory, which is our working directory, which we create randomly. Now we're going to create a bunch of agents. You'll notice that each of these agents is given a different name and a different task. And most importantly, though, it's given a different set of tools. So like our doc writer agent has write, edit, and read, but our outline or note-taking agent only has create, outline, and read, right? So we can mix and match all of the different kinds of tools for each agent, thanks to the helper functions we've created. We're then going to chain each agent through the prelude to the note-taking agent, and then we're going to build a node out of it using the same helper function we did before. Easy peasy lemon squeezy. All right. Now we create our supervisor, same as we did before. This is going to be mostly a task in repetition. The idea is that we have the same structure that we did before, but instead of being about the team that we had before, we have the team of 4, which we've created, which includes a doc writer, note taker, document editor, and copy editor. All right. Then we're going to create a big graph. We're going to first start with our doc writing state. We're just going to plop all of our nodes onto the graph. We're going to tie all of the workers back to the supervisor, and then we're going to give the supervisor the option to go to either end or any of the other workers. Then we're going to set the entry point of our graph to be our supervisor, and then we're going to compile this graph. Okay. Then we're going to display this. You can see it's the same thing that we saw before, except this time it's got 4 workers instead of having, 2 workers. Very cool. We're going to, again, wrap our entire graph in this enter chain, and then we're going to create our authoring chain. Very, very good. Then we can use our authoring chain. We can say, write an outline for a short LinkedIn post on linear regression and write it out to disk. Okay, and it does this. It goes to our doc writer who creates it, and then we finish because we've done the task. And we can look at it, and we can see, here's the outline on linear regression that it wrote. Okay, very good. It's linear regression. What more do you want, right? Now we have 2 full graphs. The first graph we have is our research graph. The second graph we have is our doc writing graph. We're going to now tie these together into a single, even bigger graph. Okay, this is going to be our meta supervisor. We got the word meta out. That's how you know it's for real. What we're going to do is we're going to build the same graph that we did before, but this time it's going to leverage as nodes each of our other graphs. Let's go. Okay, so we have to create a supervisor, and you'll notice we're giving it a whole team as the potential places for it to go next. Then we create some new state. Then we do this thing. So this is like an innocuous piece of code, right? It's just 2 short little functions. But this is what ties our graphs together. Without this, we can't tie our graphs together. We're having a sad time. Everyone's having a horrible day, right? Because our graphs can't communicate. We've now declared 3 different kinds of a state, right? So we can't just pass them around willy-nilly. We've got to have these translations, right, between different pieces of state. We also don't really care what the doc writing team did to get to the result, right? Like your manager isn't going to ask you, well, how did you wash the window? They're going to just check and make sure that you did wash the window, right? They're going to assume that involved, whatever steps you would take. I don't know, get a ladder or something, get a sponge, get some soap. The idea is we only need one part of the state. So we extract it so that we can create our final graph. Now our final graph is going to look like the state graph, just like normal. We're going to add the node. The node's going to be the research team, but we're going to wrap it in these 2 helper functions or LCEL components so that we can go from the last message to the research chain to the join graph. And we're going to do the same thing for our LinkedIn team. Then we're going to connect those 2 teams back to our meta supervisor. We're going to go ahead and build a router from our supervisor to any of our nodes, including the end node. And then we're going to set our entry point to be the meta supervisor. And we're going to create our super graph, which is going to be all of the things we've just discussed. And now we can do the thing, right? So we can say, write a LinkedIn post on the paper, extending Llama 3's context tenfold overnight. We give it some loose instructions on who to talk to, and we go from the research team. We get some research done. Wow, look at all that research. Don't you love it? Then we're going to go to the LinkedIn team, which is going to tell us that, hey, by the way, I did this thing. And then we can look at our final post, and we can see our final post has been dopified. It's got emojis, exclamation marks, hashtags, right? It's got it all. This is the final piece of the puzzle, the final connection. And again, each of these nodes are an entire graph, right? They're entire graphs. And it just doesn't matter. LangChain handles the communication for us, and we have a good day. With that, I'm going to pass you guys back to Greg, who will get us into the last breakout room of the day.
All right. Yes. Well, you guys know what's going on today. It's time for some more multi-agent systems, multi-agent RAG. You guys decide. Discuss in your breakout rooms and let us know what you think when you come back. Is it a multi-agent application? Is it a multi-agent RAG application? Is it an agentic RAG application with multiple agents? Man, there's just a lot happening out here in these applications, out on this edge. We hope you guys have a great time and you come back with some great feedback on what you want to hear more of. Multi-agent systems are something that are, quite emergent right now, and I'm quite interested to hear what you guys are discussing in your breakout rooms, what frameworks you're most curious about, what questions you have that seem like they haven't been answered by the class. There's a lot of flexibility we have to some extent with the rest of the course to really cover really edge stuff like multi-agent reasoning. And so I'm quite interested to hear from you guys what you think and what you really want to know given where we stand here today. And then don't forget at the end, when you get this LinkedIn post done, don't forget to build, ship, and share it. If you get it done, go ahead and smash it out on LinkedIn. Tell everybody you built it with a multi-agent RAG application or a multi-agent agentic RAG application with LangGraph. Tag at AM Makerspace will amplify tonight. So build, ship, share. We'll see you back to close out class in just a little bit. Welcome back from breakout rooms. It's time to conclude. We have now been through 3 weeks of this course, and we have taken a whirlwind tour of all sorts of stuff. We look today at multi-agent applications. Remember, multi-agents just means there's multiple agents, right? We learned supervisors are just routers. We learned we can have specialized agents defined by different prompts. And that's one of the main utilities of building a multi-agent system instead of a single agent system. We can separate, so conceptually it makes more sense. We can set it up like it's set up in our company instead of like a flat, one person does everything. You can kind of set it up into the individual job roles and responsibilities. And then, keep in mind all these keywords. No matter how people define agents, we're talking about the same thing: the reasoning action pattern, solving problems, crushing tasks. The environment is going to continue to evolve as we move forward in the space. And don't forget, as we continue our journey together after week 3, we are always ready to rock and roll first thing on Monday mornings, talking about what we're building, shipping, and sharing this week. Join me next Monday, 9 a.m. PT. And join Vincent next week. For those of you looking to go deeper on how to build an agent from scratch, about how to actually build these things up one block at a time, how this stuff is working specifically under the hood, this is going to be a great deep dive session for you to join. And you might be thinking, when can I join the deep dive session? Oh, here it is. Don't forget, there's lots of stuff happening on the calendar. 9 a.m. PT on Tuesday, so you can kick off your week. 9 a.m. PT Monday and Tuesday. You can find office hours. Remember, you can attend any office hours with any peer supporter. Anytime somebody's in there, jump in. Don't be shy. Ask your question. They'd love to help out. And with that, it's feedback time, everybody. Please do let us know what you thought about today's content. And as I mentioned, if you have specific questions that you'd like to have answered in the future about multi-agent systems, let us know. 2 minutes on the clock. If you have questions, please throw them in the chat and we'll get to them. Thank you, everybody, for providing your feedback. Thank you for joining us from week 1 through week 3. And really, thanks a lot again for continuing the journey with us. We've got 7 weeks to go. There's a lot of great stuff on the horizon that we're going to cover, including next week. We're going to start going deeper into some of the things. So we've gone as about end to end as we can go. So what we'll start to see now is we'll start to dig deeper into specific aspects. So when we actually do a proper evaluation with quantitative, real, robust eval numbers, what does that look like? How do we generate the synthetic data to do it? That's what next week is all about. From RAG to agent applications, we'll bring you right up to the edge, just like we did with multi-agent apps today. We do have some room also to bring in reasoning models. Everybody's talking about DeepSeek. We would be remiss if we didn't discuss some of what's really going on with you guys in this class. We just have to figure out exactly where to fit it in over the next few weeks. And also, quick shout out, if you tried to catch me in office hours today, I totally screwed that up and I went at the wrong time. I had changed my office hours this cohort from 11 to 1. So sorry about that. It will be 10 a.m. PT from now on. I won't mess that up again. And then, yeah, just thanks everybody for joining us through week 3. If you have any comments or concerns about the course, feel free to reach out to me directly if you're struggling to keep up, if you need a little help with planning how you're going to really crush the next 10 weeks. I know some folks have reached out already, and that's perfectly okay to do. And I love helping coach you guys through what it is you're aiming at, how you can achieve your goals in 2025 and beyond. I'm not in this game to take your money and then hope, wish you the best. It's like I want to see all of you build amazing things, ship them, share them, and succeed and achieve all of your dreams and goals in the 21st century, not just in 2025. So thanks again for joining us for week 3. We look forward to week 4, SDG, RAG eval, agent eval coming soon as well. We'll see you guys next Tuesday. Have a restful weekend, and you've been doing great. Just keep it up. See you soon. Bye, everybody. Have a great evening and have a great weekend.
Bye, everyone.
Thank you. Goodbye.
Have a great weekend.
Bye-bye.
See you on Tuesday, everyone. Take care.